Explaining why a set is not a basis. Explain why S is not a basis for R2. So we have this. Explaining why a set is not a basis. Explain why S is not a basis for R2. So we have this set S consisting of the vectors -4, 5 and 0, 0. So let's first see what defines a basis for R2. So if we see that in order for S to be a basis for R2, it must span that vector space R2, and S also has to be linearly independent. So we can see that if S is going to span R2, so we'll answer the question, does S span R2? Well, that will mean that it's possible to create any vector in R2 from the vectors in S, meaning if we were to take multiples of these vectors, let's say a constant c sub 1 times the vector -4, 5, plus a constant c sub 2 times the vector 0, 0, we could get any vector in R2, for example, 1, 1. Well, this would mean that c sub 1 times -4, or -4 times c sub 1, plus c sub 2 times 0, that will be equal to 1. And then also c sub 1 times 5, or 5c sub 1, plus c sub 2 times 0, or c sub 2 times 0, will equal to 1. Well, that means that -4c sub 1 will be 1, and 5c sub 1 will be equal to 1, telling us that c sub 1 will be -1/4, but c sub 1 will also have to be +1/5. This is not possible. C sub 1 cannot take on two values at the same time, which means that S does not span R2. So we've already violated the first condition. So we can say that S is not a basis for R2. But also, we can see that if we look at the vector -4, 5, if we take 0 times -4, 5, we get the other vector 0, 0. So that means that the second vector is just a multiple of the first, which means that S is not linearly independent because the second vector is dependent on the first vector. So here we see that S is not going to be a basis for R2 because S does not span R2 and S is not linearly independent. Explaining why a set is not a basis. Explain why S is not a basis for R3. So we have this set S, which has the first vector 1, 3, 0, the second vector 4, 1, 2, and the third vector -2, 5, 2. So we have two conditions that have to be satisfied. The first condition is that S will have to span V, which in this case is R3. The second is that S is linearly independent. Well, we'll take a look at the second condition first, and we can notice that if we take 2 times the first vector, 1, 3, 0, and we subtract the second vector, 4, 1, 2, well, that's going to give us the vector containing -2, 5, -2, which is the third vector. So we see that in this case, S is not linearly independent. So we've already violated the second condition, so we know we're not going to have a basis. But if we take a look at the first condition, we would have to say that if we look at c sub 1, a constant, times the first vector, plus a constant c sub 2 times the second vector, plus a constant c sub 3 times the third vector, well, if we set that equal to the vector containing all zeros, that means if we have a non-trivial solution to this, then we'll have something that will not span V. So from this equation, we get c sub 1 plus 4c sub 2 minus 2c sub 3 equal to 0, and then 3c sub 1 plus c sub 2 plus 5c sub 3 equal to 0, and then finally 0c sub 1 plus 2c sub 2 minus 2c sub 3 equal to 0. And this will lead us to the following augmented matrix. We'll get 1, 4, -2, and 0 in the first row, 3, 1, 5, and 0 in the second row, and 0, 2, -2, and 0 in the third row. And we'll put a line here to separate the right-hand side. And if we use Gauss-Jordan elimination, we'll get the following matrix. We'll get 1, 4, -2, and 0 in the first row, 0, 1, 1, and 0 in the second row, and 0, 0, 0, and 0 in the third row. So we can see from this matrix that we have no unique solution. But it's possible that we'll have a non-trivial solution, because from the second row, we see that tells us C sub 2 plus C sub 3 is equal to 0. So if we let C sub 3 equal to 1, then C sub 2 will be -1. And if we plug those into the equation given by the first row, C sub 1 plus 4C sub 2 minus 2C sub 3 equal to 0, we'll get C sub 1 plus 4 times -1 minus 2 times 1 equal to 0. And so that will tell us that C sub 1 minus 4 minus 2, that will be equal to 0. So C sub 1 will be equal to 6. So in this case, we have a non-trivial solution. And so that tells us that S does not span R3. So we see that S does not span R3 and it's not linearly independent, so that's why it's not a basis for R3. Explaining why a set is not a basis. Explain why S is not a basis for M sub 2 comma 2, the set of all 2 by 2 matrices. So we have S, which consists of one matrix with the first row 1 and 0, the second row 0 and 1. We'll consider that our first vector V sub 1. And our second vector V sub 2 will be the second matrix with first row 0 and 1, second row 1 and 0. So let's look at what constitutes a basis. So in order for S to be a basis for M sub 2 comma 2, it will have to span that space and also be linearly independent. So we'll first take a look at the second condition. We can see that there's no way to take a constant C sub 1 and multiply it by the first vector to get the second vector, because we'll get C sub 1 and 0 in the first row and 0 and C sub 1 in the second row. And if we set that equal to the second matrix, 0 and 1 in the first row and 1 and 0 in the second row, we get something that's not possible. So this is not possible. So this means that S is linearly independent. So one vector or matrix is not a constant multiple of the other. But for the first condition, S spans V, if S spans V, this space of all 2 by 2 matrices, well, that means that we can create any 2 by 2 matrix from these two matrices, meaning we can take a constant multiple C sub 1 of the first matrix, 1, 0, 0, and 1, and add a constant multiple C sub 2 of the second matrix consisting of 0, 1, 1, and 0, and we can get any matrix that's a 2 by 2 matrix. For example, the matrix with the first row 1 and 0 and the second row 1 and 0. Well, if we set this up, what will happen is when we add the two matrices, we'll get C sub 1 in the first row, first column, and in the first row and second column, we'll get C sub 2, and in the second row and first column, we'll get C sub 2, and in the second row and second column, we'll get C sub 1. And that will have to be equal to this matrix consisting of 1 and 0 in the first row and 1 and 0 in the second row. Well, from this equation, we'll see that C sub 1 will be equal to 1 and C sub 2 will be equal to 0. We get that from the first row, but from the second row, we see that C sub 2 is equal to 1 and C sub 1 is equal to 0. So C sub 1 and C sub 2 cannot take on multiple values. So in this case, this means that we have no solution, meaning it's not possible for us to get this matrix from the two matrices in S. So in this case, we can see that S does not span this space of all 2 by 2 matrices. So in this case, we see that S is not a basis for M sub 2 comma 2 because it does not span that space and it's not linearly dependent. Determining whether a set is a basis. Determine whether S is a basis for the given vector space. So we have the set S, which has the first vector 0, 3, negative 2, the second vector 4, 0, 3, and the third vector negative 8, 15, negative 16. And this is for R3. So we'll take a look at what the conditions are for being a basis. So we see that in order for S to be a basis for R3, it must span R3, the vector space, and it must also be linearly independent. So we'll first take a look at the second condition, and we can note that if we take 5 times the first vector, so 5 times the vector 0, 3, negative 2, minus 2 times the second vector 4, 0, 3, we'll get the vector negative 8, 15, negative 16, which is the third vector here. So in this case, we can see that S is not linearly independent. So we've violated the second condition, but we can also check the first as well. So if S is going to span R3, then that means we can create any vector in R3 from these 3 vectors, meaning we can take a constant multiple C sub 1 of the first vector, plus a constant multiple C sub 2 of the second vector, plus a constant multiple C sub 3 of the third vector, and that will give us any vector in R3, for example, the vector 1, 1, 1. So using this equation, we can get the following system. We'll get 0 C sub 1 plus 4 C sub 2 minus 8 C sub 3 equal to 1, and then 3 C sub 1 plus 0 C sub 2 plus 15 C sub 3 equal to 1, and finally negative 2 C sub 1 plus 3 C sub 2 minus 16 C sub 3 equal to 1. And this will give us the following augmented matrix. So we'll get the first row 0, 4, negative 8, and 1. And then the second row will give us 3, 0, 15, and 1. And the third row, negative 2, 3, negative 16, and 1. And what we can do is we can swap some rows and we can rewrite this with the first row negative 2, 3, negative 16, and 1. Second row 3, 0, 15, and 1, and the third row 0, 4, negative 8, and 1. And using elimination, we'll wind up with the following matrix. The first row will be negative 2, 3, negative 16, and 1. The second row 0, 9, negative 18, and 5. And the third row 0, 0, 0, and negative 11. And this third row tells us that 0 is equal to negative 11, but that's not true. So this is not possible, meaning it's not possible to create this vector 1, 1, 1 from the 3 vectors in S. So that tells us that S does not span our vector space R3. So in this case, S is not a basis for this vector space because it's not linearly independent and it does not span R3.
Determining whether a set is a basis. In the exercise, determine whether S is a basis for R3. If it is, write U is equal to 8, 3, 8 as a linear combination of the vectors in S. S is the vectors 4, 3, 2, 0, 3, 2, and 0, 0, 2. So we first set up the equation C1 times 4, 3, 2 plus C2 times 0, 3, 2 plus C3 times 0, 0, 2. We set this equal to 0, 0, 0, which gives us the following homogeneous solution. 4C1 is equal to 0. 3C1 plus 3C2 is equal to 0. 2C1 plus 2C2 plus 2C3 is equal to 0. So going through this, if we look at the first equation, this implies that C1 has to be equal to 0. Plugging this into the second equation, this implies that C2 has to be equal to 0. And plugging both C1 and C2 into the third equation, this implies that C3 has to be equal to 0. Since the only solution is the trivial solution, S is a basis for R3. So next we solve the equation with plugging in the value of U. So we will have 4C1 will be equal to 8. 3C1 plus 3C2 will be equal to 3. And 2C1 plus 2C2 plus 2C3 will be equal to 8. Looking at the first equation again, this implies that C1 is equal to 2. Plugging this into the second equation implies that C2 is equal to -1. And plugging this into the third equation implies that C3 is equal to 3. Therefore, we can write the vector U as the linear combination of 2 times 4, 3, 2 minus 0, 3, 2 plus 3 times 0, 0, and 2, which is equal to the 0.838.